that gives a skew which eliminates some kind of harmonics in the torque and reduces pulsation, which can be better from model analysis perspective, structural perspective. So this is one element. Another element is the life of electric machine. So the life is here very important, because the definition of life is here is how many miles, how many miles I can run. This, what is a life? So there, this is a typical. I mean, this is a very different environment at an industrial application where we have more vibration, shocks, thermal extremities, because we will do some hill start, very high gradient start. We will pull up for some time. Their duties are different, right? We will need peak performance at various conditions, and it should be less maintenance or no maintenance, say less wear and tear we expect. So it gives us a different say different specification for the material to be considered when we consider the electric steel as such, say for example. So the at high speed, because this is a like 12,000 rpm, 15,000 rpm, 18,000 rpm. So those laminations, those rotor laminations, because we have narrow bridges there, those all has to hold those windings or magnets. So those all puts a lot of constraints on what kind of a steel, what kind of a Pascal scale we should have, the stresses and strains on coming on the material. Those also we have to consider when we design a machine, and that ultimately drives the life as well. Thermal consideration, like how well we cool the machine. So and how we arrest different failure modes, like these are the different failures that happens, and those we have to reduce it to the best possible numbers. So we have to set these numbers when we start designing this electric machine. So you can see whether how we can reduce this turn to ground, turn to turn. What are the ways that we can overcome this or eliminate this, if not if the design allows that to eliminate some of the faults, or how we manage the fault conditions, say in when the vehicle runs and abruptly something fails, how the motor should be protected, what kind of mechanisms we should have in inverter to protect or isolate the machine, right? So there are different fault conditions that we have to consider as well when we design road conditions, actual life conditions, that how we should recover the vehicle once it fails, whether we can tow it, because it will generate some electricity. It's a generator as well when we have permanent magnet. How we can tow it, what kind of voltage it will generate when we tow it at high speed, what are the towing conditions. Okay, those all consideration goes in machine design as well, along with the life. So we have seen a lot of other parameters, or it's a wide uh, uh, say a set of parameters that we have to consider for electric machine. Coming to the inverter, the latest trend is a wide band gap switches, that is SIC that we call. And you can see this is a conventional on left hand side, it's a conventional inverter. Now it's more compact with SIC, and also you can see the efficiency is much better and higher with SIC. So the silicon, this is IGBT performance, the dotted one, and the solid one is a MOSFET. So this is the output power versus efficiency, and you can see we get a the claims are very good. I mean the whatever the, if you compare the SIC for the same almost same power, you can see their volume density, power density are much better, and it gives like a something breakthrough to the requirements that we have for the traction. So these are predominantly, these are considered nowadays everywhere. Almost every OEM is focusing here on silicon carbide MOSFETs, and those are some these are some deployed also. Some you can see there are many say tier one supplier claiming that we have these already in place for inverter and converter, and those are commercially available. It's no more like just an university level research, but it's all bring to the factory now from university. Those gives a lot of benefits because the switching losses, the conduction losses, the switching losses are predominant. I mean, it's very less. They are much thermally stable, and because of this behavior, we can have a totally different switching topology or different switching strategy across the speed. So say this is a frequency or a speed on the x-axis, and this is a carrier frequency. So we can see this is a conventional on the top, and bottom is a new one, that is a SiC. So we can push very hard to the high speed here, and then we can change the our switching topology from say PWM to say 6-step or say triple pulse, okay, a single pulse here at very high speed. So this gives us a lot of say benefit in terms of eliminating or reducing some harmonics, which in turn help us to even reduce some losses in machine as well. So you can see this also the impact on the machine is coming from the inverter side, which is you can see the losses are drastically reduced, and definitely that means your efficiency will be much higher compared to the conventional one. So this gives us the another dimension, that not just machine but also the inverter also has to be considered, and what kind of a topology that we are using. So this is typically 6-step control, which we try to implement at very high speeds, because that gives us very good say voltage, but a lot of harmonics at that speed. But there are a lot of versions that comes up, and it drives also to the space vector, right? So this is a say birthplace where where the space vector is evaluated. So you can see this is where instead of switching to the 6-step rotating. So this is a space vector modulation that we typically implement in our FOC, right? Field oriented control. So this control strategy is also impacted in the design of a machine. What kind of a control strategy that we will have. So this is let's go to the control now. So what we want, these all AC machines, we want to operate like a DC machine, because DC machine, you can see the flux and the torque elements are, or the flux producing current and the torque producing current are decoupled, because we have a field current and we have a separate phi here. So flux, and this is the armature current. So these they are independent, they are quadrature in nature, and that is where we AC machines are gives a lot of challenges. So field oriented control, that is FOC, try to make our AC machine behave like a DC machine from a control standpoint, so that we can control AC machine like a DC machine, where we can control our ID, direct current, direct axis current, and IQ current, the quadrature axis current, where they are like this kind of a topology, right? So in DC machine, there are, this is the beauty, because at high speed we don't want the much flux, because that creates a lot of back EMF, but we want torque. So it's a trade-off. So if you are, if we can decouple this, we can really control whatever we want at a high speed. So at high speed, the back EMF is so high that it may be more than VD, that bus voltage, right? So to do that, we demagnetize the magnet, or we call the we increase the ID. Okay, so the moment we increase this demagnetizing component of current, the flux starts dropping and the speed starts increasing. Then we can increase the speed, but definitely torque will have penalty on it, right? So we cannot have the constant torque in that region, but power we can maintain because speed is increasing. So the purpose of this field oriented control is to have a very good say control strategy. So field oriented control, we try to make the so it's a mathematics that we have to put that the mathematics will allow us to do that the FOC. So this is, we can see that um, the it goes from the ABC to alpha and beta, and then go to the ID and IQ. So these are all called Park and Clark transformations, which are nothing but mathematical in nature. But we can see that this mathematics allows us to go from this AC nature to DC nature, right? So the thing is, we can go from this nature to the this particular nature, you can see here. So this is a representation that if we jump on, if we jump on the rotor, instead of if we look at this say machine from a stator, if we stand ourselves on a stator and see, it will look like a sinusoidal. But the moment we jump on a rotor, we may look like okay, something is stationary, like IDIQ, like a DC type of machine. So the rotating reference frame is something critical. Is something that is what we want from this all mathematical operation, right? So that we can control this like a DC machine. So this is where FOC topology would look like. So the software bit, hardware bit, internal and external. So what we need, one resolver, or encoder. We mostly use resolver, is sturdy nature. And then we have a current measurements here, and the angle. So this is the angle and current, and we have a position loop and a speed loop and a current loop. Okay, so this is what we can also call torque loop. Say current loop is a torque loop. So then we have a PID typical regulator here, say control strategy, whatever typically what we have, the reference is coming from here. And the this is our FOC part, that is a Park and Clark, where it transforms from say alpha beta to D and Q, say. And then we can also have the our space vector PWM strategy here to get the generate the so this is a driver here, so which will generate the pulses PWM to the this IGBT or MOSFET, whatever we have. So this is how is a FOC. We will be driving on this deep dive, all these different elements that I am talking now. And this all will impact overall machine. Okay, the speed, you see the speed here. We are very much limited by this topology. If we do some more modulation by injecting some say third harmonic, we can do better, give maximum speed, right? So the same motor can behave in a different manner when we introduce this machine in a different switching topologies, right? So this is also as a machine designer or a machine or electric drive person, we should also look into these aspects. And then we have to see what kind of harmonics we expect. Okay, so how they generate PWM is through carrier and this sine wave. So this is what we are more keen, what kind of a frequency this has, because those frequencies will have the harmonics around that. Okay, so we can see the harmonics are in the multiples of this carrier frequency. So those frequencies, we have to see if those are eliminated, or those are not seen by the machine, or they are filtered when it enters. A machine may also filter because it's a big inductance, right? So it may also filter some of the harmonics. So it's a again a study together. Also, we have to make sure there are no low order harmonics which are again detrimental in nature. So those also we have to see when we do FFT on the output of the inverter, or the strategy that we have implemented for the switching. So these modules will look like this. You can see the DCP. These are all we call either a module or a brick. Okay, these days they are saying they are get rid of these bond wires, because this is the most critical delicate element where it used to fail. So there are different technologies that are being claimed that they are becoming better and better. And you can see this is where we will be thermally looking into this brick or module. This is where we are mostly interested, is a junction temperature of the IGBT or a MOSFET. So this temperature is where is something very critical for us, because there is a specification where we have to be careful about this specification on the data sheet, right? So these are the case temperatures that we can see here, that we can measure here. But though there's some relation we have to establish between junction and the case temperature, if we don't have a right mechanism, and we have to protect it, right? So this is a trend, overall trend you can see in the, so definitely SIC or GN are the way forward. You can see the voltage is also much better, efficiencies and temperature sustain whatever by the wide band gap switches are much higher. So we are moving towards, slowly towards that region. So the important thing is system efficiency. At the end of the day, is what is as a vehicle, as an electric vehicle, what is important is all these losses put together: machine, inverter, converter, battery. This is what the system efficiency is all about, right? So we have to make sure that they are not just at their peak efficiencies, but wherever the maps. So each every entity or every component has efficiency map. So machine has got, say, higher efficiency in, say, higher speed or medium speed. Maybe inverter may not have efficiency in those region, right? So overall, we have to see how we can get a better efficiency, and we have to calculate at some point how much say kilowatt hour energy, because not just power but also energy that we are asking, demanding. So efficiency wise, you can categorize those, you can see the losses here, those are pretty high. And even you can see the efficiency, but overall efficiency you can see 80%, typically 79, 75. These are the some ranges that you can see in at particular some drive cycles that they can give us. So these are the you can see that they are the thermal different thermal topologies that being considered, because thermal is something poses a bottleneck in terms of getting more efficiency or driving the inverter and the machine at some particular point where it is having sweet spot. So the you can see at different the manufacturer had different cooling strategy, or how they are using this, say, passive cooling, water plus glycol, active cooling, some refrigeration cooling, oil cooling. So somebody has maybe different, so these are all the cooling strategies by used by, this is little bit old, but this gives some direction that how the cooling is being addressed or done. Okay, so we'll have some session on these only, say, thermal aspect of machine. So these are the some challenges at the end of the session. We come to a conclusion on this. Some challenges that we have to consider, that okay, cost, weight, volume, reliability. These are the elements that we have touched upon, and I try to give some flavor of it as a machine designer that we have to consider. And we will have to deep dive this when we consider electric machine design as such, or electric drive as such. Okay, and by the way, the best practice is to design electric drive, because they integrate, if they integrate well, we get a very good operational efficiencies, right? So the some last thought from me. So we have to consider constraints from all directions, from battery, from inverter, what kind of the strategy, winding strategy we should have, the rotor design. But the thing is, rotor design and winding strategy is a bigger space in this all this design area. And harmonic is definitely something that we have to keep on monitoring when we select this, make when we do trade-off analysis. Thermal performance is key. Battery inverter machine efficiency, we should always keep on watch on this, how their maps are. Transmission, how the transmission is being sized, and then we have to accordingly size it. Vibration, what kind of a vibration we are generating, and what kind of a say noise, because harmonics are also responsible for EMI, right? So the architecture, right? Overall architecture, how it impacts. We have seen that, right? How DC-DC boost converter, what is the voltage that is available to us as an architect from the architecture. Failure modes we have seen, right? How those will have an impact on our machine design and the life, right? So at the end, I just want to give you these that. Opportunities are many there because there are a lot of challenges. It's a multidisciplinary in nature, and we have to give a system approach to this. So it's a multi physics kind of a thing. It's electrical, mechanical. There is a the fluid, the cooling element, thermal element in it. There is a system approach, like because in vehicle we need what kind of requirements we have, right? So system approach, architecture approach is very important. So these challenges actually brings a lot of opportunities as well in this area to do research, and you see a lot of people are doing research and design in this area, and many OEMs are considering this as a in-house design rather than giving it to tier one, because this is something critical. They want to make sure that their vehicle, because this is a key element in this whole, which is driving the whole vehicle, right? So they want to make sure we are approaching this design in all directions, all possible directions, and we are addressing those requirements appropriately. So there is a good mix right now. OEM are also, but majority of OEMs are trying to bring this machine design in house, and tier one is also, or they are partnering very closely with the tier one suppliers. So they may give design to the tier one to say manufacturer, or ultimately they want to have very good understanding on machine. So it gives a lot of opportunity as well for say traction drive people. And off the shelf is not really a successful so far. I have not seen that you just buy something and plugins and then it works, but it's very difficult that way. We have to do a good amount of customization, and a lot of trade studies goes into it. So finally, it's a really boiled down to the design, and not really off the shelf. It's still not a commodity as such.